Okay, so last time we saw that the average rate of change of a function is given by f of b minus f of a over b minus a. So this is the key equation when you're computing the average rate of change, right? So it's literally the change in y over the change of x. So you can think of this as delta y over delta x, where we've previously identified delta y as f of b minus f of a, and then the delta x as b minus a. So over a specific period or interval, the average rate of change of a function is just given by this change of y over change of x. So in this lecture we have an example. So our example, we have a car and it's driving on the highway and it passes mile marker 120 at 3:30 p.m. and then it passes mile marker 291 at 5:45 p.m. So the question now is, what is the car's average rate of change of its distance? So let's say x of t represents basically the position of the car at time t. So it's a position, and we should specify it's a position in miles, and then time t in hours. So x of t is in miles, and t is in hours. So we want to understand the average rate of change of this function. Now, as it turns out, the average rate of change of this function is simply the car's average speed. So the average rate of change of this function x of t is simply equal to the car's average speed over that period of time. So let's see what the average rate of change of x of t is, and we'll understand why it's the average speed of the vehicle. So the average rate of change, we have to apply the formula. It's just going to be x. We can say that t is hours since 3:30. So let's set 3:30 p.m. to be the 0 point for the t-axis. So this is going to be, okay, we have to do a little conversion. 3:30, 4:30, 5:30. 5:30 will be 2 hours later. 5:45 is an additional quarter hour. So we're looking at x at 2.25 minus x of 0 divided by 2.25 minus 0. So we have the change in distance divided by the change in time. So x of 2.25 was 291 miles minus x of 0 is 120 miles. We always add or subtract like units together, so we have miles and miles. And divided by 2.25 minus 0, so it's 2.25 hours minus 0 hours. We get 2.25 hours. And let's just, oops, that is not correct. It's miles on the top per hour. And when we divide this out, we get 76 miles per hour. So the average speed of the car, or the average rate of change of the car's position, 76 miles per hour. Now what does this mean? Does this mean that the car was traveling along at a constant rate of 76 miles per hour? No, it doesn't. The car could have been going 100 miles per hour, then it could have slowed down to 50, then it could have been going 80, then it could have stopped for half an hour at a rest stop, and then it could have sped up again. It could have gone backwards the other way. Any number of things could have happened over this 2 hour, 15-minute period of time. We know that the average speed is 76 miles per hour. Now, in the previous lecture, we mentioned, let me draw this generic function again. Let's make it a little bit more wiggly. So in this time, let's call this the t-axis, and let's say this is x of t. So this is our position as a function of time. So this guy is going back and forth and up and down. every which way. If we have 2 points, we said that the average rate of change represents the slope of the line connecting those 2 points. Now, what does this mean in terms of this example with position, time, and speed? Well, it means that the straight line connecting the 2 endpoints is the line that you would be along if you drive at a constant speed. So this line has a slope of 76 miles per hour. Say, why does the line have a slope of units miles per hour? Well, the vertical axis, x, is in miles, and the horizontal axis, t, is in hours. So when we divide change in the vertical displacement by the change in the horizontal displacement, we get miles per hour. So we have this line connecting our 2 endpoints. It has a slope of 76 miles per hour. And that line literally represents, if you're driving along, if you were to drive at a constant rate and still be at mile marker 120 at 3:30 p.m. and still be at mile marker 291 at 5:45 p.m., what would your trip look like? What would your trajectory be? Where would you be as a function of time? You would be along a straight line that's changing at a constant rate. The constant rate is 76 miles per hour. So you can see that the average rate of change, what it actually represents is, if instead of doing some crazy up and down thing, if you were to actually just change at a constant rate, always changing at the same rate, nothing interesting happening, never speeding up or slowing down, but you still start and stop at the same place, what would that rate be? And that's really what the average rate of change means.